Hi everyone, welcome to week 5 of Techquitable. Today's lesson will be on stacks and queues, and it will be presented by Alma and Carissa. And Alma, do you want to take it away?
Yeah, sure. So, a little introduction to me and Carissa before we dive into the presentation. I'm Alma. I'm currently a software engineer at Notion. I graduated from Dartmouth, I guess. And I joined Notion not that long ago. So, I was doing the interview process within the last year, going through what you guys might be going through at the moment. And excited to be talking about stacks. Krista, do you want to give a short intro?
For sure. Hi, I'm Carissa. I currently work at Square as a software engineer. I've been there for about 3 years now. And I had a kind of unusual and winding path to software engineering. I originally got my bachelor's degree in music with a minor in math. Did everything from teaching high school math to serving coffee, scooping ice cream. I was an audio engineer for a while, and then realized that I had always really loved programming, wanted to go into that. So am mostly self-taught, took some community college courses, and landed an internship. So an unusual path, but very, very happy to be here. And yeah, excited to talk with you all about some stacks and queues, I guess.
Yep. So, like we said a moment ago, today's topics will be stacks and queues, which are pretty similar data structures building upon the linked list that you guys covered in last week's lesson, I believe. Um, in general, they're both relatively simple data structures, but have a lot of applications in terms of being solutions to the kind of programming questions you might see. So starting off with, what is a stack? It's a relatively simple data structure with a pretty simple interface, and you'll see it used in things such as depth first search traversal, and checking if things are balanced. So we'll be going over a problem that uses a stack as a solution, and it'll be clear how a stack could be used to check balancing parts of a problem. So before we go too deep into the actual what is a stack by strict definition, I think it's easiest to understand a stack in terms of things in your everyday life. So the analogy listed here was a stack of plates in a cafeteria. It's a collection of items that you put on top of each other, but you can't, anything you put on top, the first thing you put on top has to be the first thing you take out. So last in, first out, that's what it refers to. Another analogy I was thinking of would be a can of Pringles. So for example, when you're filling up a can of Pringles, the Pringles you put in last are the ones you'll be eating first. And at some point, the can of Pringles can get full or it can get empty. These are the kind of operations that you can perform on a stack. And instead of being each item in the stack being a Pringle, it could be whatever you want the stack to be implemented. So given the idea of a stack, there's a more strict set of operations that a stack needs to support in order to be defined as a stack. The first one here is push. That's when you add an item to the stack. So I'm going back to the Pringles analogy. When we get a can of Pringles, it's empty at first. The manufacturer needs to add Pringles to the can. Adding each Pringle would be a push operation, and the can has to support, I guess, like pushing a single Pringle on. And this is done in a time complexity of O of 1 in a stack. Like I said, the can at some point can get full, that is known as the overflow condition, when you can't add any more items to a stack. That, not any questions so far, I guess? Cool. So the second operation that's a stack has to support is called pop. And would anyone be willing to give like an example analogy for what like popping from a stack could be? Anyone in the audience?
Like taking out the top Pringle.
Yeah, taking off the top Pringle. I'm really latched onto Pringles at the moment. Can anyone think of other things in their life that could be an analogy for a stack, or where you could see a stack in everyday life?
Pancakes?
Pancakes? Did someone say pancakes? That would be
Yeah,
perfect.
I
Yeah.
said, yeah, I said pancakes.
Yep, that's exactly right. You can add pancakes to a stack of pancakes, or then take off a pancake from the top, but you could try to take a pancake from the middle, but it probably wouldn't work out very well. At some point, the stack of pancakes could run out, and then that's known as the underflow condition when the whole stack is empty. So both these operations, push and pop, are O of 1 operations in a stack. Some other operations that a stack commonly implements is being able to check just the top element without removing it. So like you can see in a can of Pringles, if there's an actual Pringle left and what the Pringle looks like, that would just be the peek operation, but you don't have to touch it, either put it on or remove it. Typically, a stack can be implemented such that it supports the standard array operations, so knowing how many items are in a stack and if the stack is empty and whatnot. Okay, so before we dive into the problem, does anyone have any questions or thoughts so far that they want to ask about?
I'm a little bit confused about like the definition of the stack, because I see the line like last in first out on the right corner. So I guess that would make pancakes or Pringles not exactly the right fit for the definition, no? Because I thought stack would be whatever you put in last, you take out first. Like if you are organizing clothes in a drawer or something like that. So you would take the clothes that you put on top out first.
Mhm.
So it's
Yep.
I see how it can be applied to Pringles now. Okay, sorry.
Yes. Yeah, I guess in my definition of Pringles, I'm assuming the can has a bottom first and it's not like funneled through. Maybe I think that the pancake example or stack of plates works a lot better, where there's like a clear ground, and there's no way you can like kind of subvert going through the ground to get the item you put in first. So last in, first out. I like the clothing drawer analogy as well. So one common type of problem that stacks are a really good data structure for is whenever you want to check that something is balanced or there's like a matching set. So this problem here, valid parentheses, asks us to determine if a string is, if it contains valid parentheses, which is defined by any open bracket being enclosed by the same type of bracket. So I'm gonna stop the sharing a screen so I can type a little bit to give some examples of what, oh, there are examples on the next page. So we'll go back to presenting. So the string here is this parenthesis or the string here is just going to be a set of characters, and the only characters will be brackets. So in this example, there's 6 characters. Oh yeah, there's 6 possible characters that can be in this string, and then all the characters are types of brackets, either opening the circular bracket or the square bracket or the curly brackets. So in these examples here, the first one is clearly a valid set of brackets in that there's a a circular bracket, a round bracket, and it's an opening bracket, and then it has a matching closing one, and nothing's broken in the bracket. I'm going to jump to this first false example. Does anyone want to explain why, or does anyone understand why this is a bad set of valid parentheses? The square bracket, circular open, circular close, and then square open.
It's invalid. I think it's invalid because you tried to close a bracket even though you haven't opened one.
Yeah, exactly. Yep, so that's pretty much the condition we want to check for when. So yeah, like you said, when there's an attempt to have an open bracket, or when we're trying to close a bracket when the opening bracket has not happened yet. Looking at the second example, or second false example, does someone want to explain why that's a false set of brackets?
I guess you open a parentheses, then you open a square bracket. You try to close the parentheses, but you can't do that until you close the square bracket you opened.
Yep. So the other condition is making sure that the bracket is closed before starting a different type of bracket. So that's exactly it. And then the last one is the third kind of like false condition. Does anyone else want to explain why this one is like a false set of parentheses?
This one's false because the very last ending bracket doesn't have its corresponding beginning bracket.
Yep. So there's an attempt to close, similar to the first bad example, there's an attempt to close brackets without having an opening bracket of the same type happen. So in a fashion, I suppose, the first invalid case is like a similar version to the kind of error that we're seeing in the last invalid bracket case. So thinking through this problem, stacks are useful here to check balance. And here we're checking that a closing bracket, when it happens, we have to have seen a opening bracket of the same kind before. That's, I guess, like the main condition we're checking. As a consequence of that, every time we see an opening bracket, we have to make sure we remember that opening bracket and then what kind it is until we see the closing bracket. That as a high level, just like audibly, is what we're trying to solve for. And then we're going to be using stacks to implement that storage of information. So we're going to just jump into the solution just so we could see where a stack is used. And then hopefully this type of problem is quite common. So there's some example problems we could go through after, maybe, that we won't just give you the solution. But the gist of this type of valid balancing parentheses problem, in terms of how it's solved, is you go through the string, and then when you see an opening bracket, you have to remember that you see this opening bracket and what type of bracket it is. So in order to do that kind of memory, or I won't use the term memory because that might get, I guess, like time and memory complexity confused, but in order to remember that we see a particular type of bracket and that it's open, we push it onto the stack. So when we were describing the cases where the string failed, the things we were checking for were that we had seen an opening bracket of the same type before. Because we have pushed it on the stack already, when we see a closed bracket, we check that on the stack is a matching opening bracket. So that means a bracket of the same type. And then we can pop off the opening bracket because we no longer need to remember that information. So the last, I guess, like case in the false examples was if we were using a stack here, we would push onto this, or we would see first this opening square bracket. We'd push onto the stack a square bracket. Then we see another opening round bracket. We push onto the stack that round bracket. Then we see a closing bracket. Then we can pop off the round bracket. Similarly, when we see the closing square bracket, we check the stack, see that there's a square bracket that we already stored, we could pop that off. And then at the end of the problem, there should be nothing left in the stack because every opening bracket should have a corresponding closed bracket. So the stack should be empty. So there's a walkthrough of how the stack works in the solution with a bit clearer of an example, I suppose. So here is, here's an example string where as we go through each character in the string, this is what the stack looks like at that given time. So for the first character, we are pushing on this round bracket. So the stack looks like just this one round bracket. At the second step, we push on just the square bracket. Similarly, the stack then becomes these two items of the round bracket and the square bracket. Same, I guess, like same process for the curly bracket. And then once we reach closing brackets, then we start taking things off or popping from the stack. So when we see a closing curly bracket, we check the stack has on it a corresponding curly bracket, then we can pop off that bracket. Similarly, when we see the closing square bracket, we pop off the square bracket we'd seen previously, and then opening bracket, we push. We don't do any kind of checks when we push. And then closing bracket, we check that the stack on top has the right type of opening bracket. Then we pop, and then closing bracket, check again what's on top of the stack, then we pop. And at the end, the stack is empty, so we know that the string has passed this check for valid parentheses. This is the example that we described earlier. That is when there's an attempt to close or to open a different type of, or I guess close a bracket of the wrong type. And it fails when we get to, I guess, the third character in the string. So at the third character, the stack looks like this round bracket and a square bracket, and the character we're checking is this round bracket. So when we check the top of the stack, what we expect or what needs to be there is a round bracket, but instead we see a square bracket. Because there's a mismatch, then we know that the string is invalid in terms of parentheses and return false. So this is the this is the example where the stack isn't empty. So I'm gonna just add a big blank square here, and then maybe we can go through building the stack character by character. So at this first character, which is a square bracket, what do we do? Who wants to call out what the stack should look like?
Well, you should add that. So we see an opening brace,
Mhm.
so we add that opening brace to the stack.
Yep. What kind of bracket am I adding to the stack?
The square bracket.
Yep. All right, so the next is this round bracket character or opening round bracket. What does this, or what do we do to the stack at this step? Who wants to, you can also call out in the chat or out loud.
Do you push the round bracket to the stack?
Yep, that's correct. All right, now we're at a round closing bracket. What do we do to the stack? What two things do we do?
We pop the opening round bracket.
Yep. And what else are we doing when we're popping? We're not just mindlessly popping, right?
We check to see if they're the same.
Yep, that's correct. So we check that they're both round brackets, and then we can pop off the round bracket, the round opening bracket. And then we're at the end of the string. What's the last thing we wanted to check?
We check if we have anything in our stack, and if we do, then return false.
Yep, that's correct. So we're at the end of the string, but there's still this one square bracket left in the stack. And as we can see from the actual example, this isn't a valid string. So we just return false, which is the correct answer for this problem. Okay. So this is the implementation for the solution where a stack is implemented as a linked list. And I believe this is just in Python. But you guys can go back and refer to these slides and look at the solution in code. The general gist is any type of problem you see where you're doing some kind of like matching of some sort, you'll see stacks being used pretty commonly as like a way of verifying that the next, I guess, item has like a corresponding pair of sorts. So that might have been a lot of information. Let's take a moment, I guess, to pause and open up for questions if anyone has any.
I had a question.
Mhm.
Like, would it make sense to also like, if we have a palindrome, would it make sense to also use a stack for some cases?
Yeah, that's a good question. It would really depend on the problem. So I could totally see a problem that asks you to check, is this a palindrome? And one way you could do it, I guess, is adding items to a stack. But at some point you have to know the inflection point of the palindrome, or like when it flips. And I'm assuming you already know the length of the palindrome string. So it's not necessary to do a stack there. It's more when you're, so the answer is you could use a stack there. You don't have to, but it would be a very valid way of like implementing. You add the first half of the palindrome to the stack, and then you can check the top of the stack as you go through the rest of the string. That would be definitely a possible solution.
Okay. Yeah, just Dario brought up like if a palindrome has an odd number of characters, then it may not work, which makes sense.
Mhm.
Yeah. But yeah, thank you.
I also had a question.
Mhm.
I was wondering like about the time complexity. I didn't really understand why pop is O of 1.
Mhm.
I understand if it's like you're just popping like one, like the top of the stack,
Mhm.
but what if you just want to completely empty the stack? What would it be then?
So because each pop refers to just removing the topmost item of the stack. If you want to empty the stack, you have to perform pop on each item in the stack currently and say the stack is of length n. What would you say is the time complexity then of emptying a stack of length n?
Probably O of n.
Yep, that's correct.
Okay, thank you.
Any other questions?
For the solution, I just want to make sure. So the very last if statement, where it's like if C is equal to a closing round bracket, and then it says repeat for the squiggly, and then the square bracket. That require just more if statements. I just want to make sure, since this
Yep.
one would only work for the closing round bracket.
Yep, that's correct. So this if statement would just be repeated 2 more times, where instead of having the round brackets, we'd have the curly brackets and the square brackets.
Okay, gotcha. Thanks. I
Yeah.
just wanted to make sure.
Yep. I might edit this slide after and just write out the repetition so it's a little more clear. But
okay, thank you.
Would you consider mapping every opening bracket to their matching closing brackets, that you don't have to have so many if statements?
Yeah, there are definitely more clever ways of going about writing this. It functionally wouldn't make too much of a difference. So if we wanted to maintain a mapping of all the round brackets to their corresponding closing brackets, we could have like a constant at the top that's just like round brackets, and then it being like the curly bracket and the closing bracket. Functionally, it doesn't make too much of a difference. It would just be clearer in terms of writing the code. Yeah,
All right,
so
thank you
that
so much.
would be like a it would just be like a cleaner and like more clear way of referencing these kind of brackets. So I mean, I would be really impressed if I saw that and saw someone kind of think about that, but definitely don't stress it in terms of if you ever find yourself in an interview setting, like refactoring and making code more readable is like fantastic, but also by no means like necessary or like required or anything.
That makes sense. Thank you so much for your input.
Any other questions?
Yeah, it's not necessarily related to stacks, but I was just looking at this and wondering if it would improve the algorithm to have like just to check the length before you go to the for loop, and if it's like odd, then you just return false.
Yeah, that would be a quick way of checking. Let's see, would that fail? I think, yeah, so in this particular problem, because the only characters we have are the bracket characters, that would be a pretty valid way of just like quickly exiting the problem in those like odd cases or odd number of character cases. So that'd be pretty cool to see. One thing to note is this problem might come up where there's other characters in the mix. So instead of just having the brackets, it would be a set of characters like letters and numbers and also the brackets, but you want to just check for the valid parentheses case. So if you ever see a version of the problem that looks like that, keep that in mind. But for this particular iteration where it's just the bracket characters, no spaces, no letters, no numbers, then checking the length of the characters would be like a great way of like exiting without having to run through the whole string every time.
That makes sense. Thank you.
Does anyone know what the time complexity of the solution would be? Say S is going to be an array of characters of length n. What's the time complexity of this like particular solution?
It's just O of n, right? We're just iterating through the array once. So.
Yep, that's correct. Cool. So I'm now going to pass the baton over to Carissa, who's going to be covering queues and a practice problem with queues.
Awesome. Okay, sweet. Sorry, Alma, how did you, whenever I share my screen, it's pausing my audio.
I can also drive if that's necessary. Or you...
Sure, yeah, I can just tell you when to move forward.
Mm-hmm.
Yeah, I usually use.
You can also try maybe one more time.
Yeah, are you sharing your whole screen or just a tab?
I shared my whole screen.
Okay, maybe I will just do that. Can y'all still hear me?
Mm-hmm.
Excellent. Okay, let's do that then. All right, so now we're going to talk about queues, which is kind of a similar but different in important ways, data structure from stacks. Obviously, this is important where ordering is important. Queues are different from stacks, importantly, in that instead of last in, first out, we get first in, first out. It's actually just to give y'all a quick overview. Some like obvious comparisons would be a cafeteria line, or a line at your local coffee shop. If everything's working right, the first person in line should be the first person that gets served. Printer queue, or really any kind of like queue on your computer, is going to use this model as well. We always want the first thing that's added to be the first thing that is executed. And although sometimes it doesn't feel like it, customer support queue, we could also put that in there. Although sometimes it feels like they don't get to you until they've served every other person. So this is important in tasks where we really need to keep that order, and especially where the length of time between where something is added to the queue and where something is executed is important, to keep that as short as possible for everything. We always want to serve the first thing that was put in, and keep this constantly rotating queue. Sweet. And obviously the main operations here are just going to be similarly to stacks. We're going to have the push operation, which will add a new item. Importantly, we don't have a stack of plates. We have, I don't have a fun analogy for this, unfortunately. I don't have a Pringles analogy, but but we have, a line of people. When we add someone to the line, we always add them to the end rather than, the top or the front. And when we dequeue or we pop something off of that queue, we remove an item, and that's from the front or the head of the queue. Any questions? I'll pause right there just for any questions on sort of the basics on how queues work. Awesome. A few other operations we might want, similarly to stacks, we might want to just peek at the first element without actually removing it, just in case we have, logic derived from what will happen when that object is removed. We may want to know the size of the queue. That could be especially important. If you have a queue of messages, you want to know the size so you can monitor if it gets too long and something's gone wrong with the system, or you need to, help it out in some way. That would be super important. And we just want to know if it's empty. So there are two ways, at least two ways we're going to talk about for implementation right now. There are probably infinite ways you can implement this, but these are just using data structures that you already know. One being a linked list based implementation. And again, ordering is important here. So the head of the linked list is going to become the front of the queue, meaning that when we add things, we're adding them to the rear, and then we're taking things from the head. And you can kind of imagine how that happens in code. We find the rear node, we add the pointer to the thing that we're adding, and we make the new node the rear. And then when we want to pull something off of the queue, we just pull the head node and we make the next node the head. And we can also use arrays. Now, arrays are used most often for stacks. So we get some kind of different time complexity by using arrays, and we're actually going to go into that implementation right now just to see how we can use an array to build a queue. Now, when we do that, we have two choices. Unlike a linked list, like an array, you could do it either way, technically. You could make what is the terminology here? The front of the array, the zeroth element of the array. You can make that the front of the queue and then queue things to the back of the array and take them off from the 0th element and shift everything over. Or you can enqueue things to the top of the array, like insert something in the 0th position, shift everything over, and when you dequeue, you take it from the end of the array. We're going to make the front of the array, so the 0th element of the array is the end, which means that when we insert something, that's where most of the time complexity is, because we're inserting something at the 0th position and we're shifting everything else over. But that makes the pop or dequeue operation a lot easier because we just take something off of the end of the array. So reading through this array-based implementation, pretty straightforward. When we initialize the queue, we just initialize an array. If we want to check if it's empty, we just check if the array is empty. I will also say there's another notation in Python that you could just return not self.items. Python is, when Python evaluates a list as a Boolean, it tells you whether or not the list has elements in it. So we could simplify the statement even more, but this one works as is. We just check if the array is empty. When we enqueue something, this is probably the most complex operation for this queue implementation. When we enqueue something, we have to insert it at the very first element. Thankfully in Python, there's a nice little insert function, and this does all the work for us. But notably, this is going to have time complexity O of n, because we're not just adding something, we're putting something at the 0th position and shifting the position of everything else in the queue. But that lines us up to have a very nice and simple dequeue operation. We just pop something off the end. And of course, if we want to know the size, we just return the size of the list of items. Definitely going to pause here because I know that was a lot of information. Any questions on this array-based implementation of a queue?
I got a question. When would you use like the array implementation like over the linked list implementation?
That's a good question. We'll see in the next slide, and we'll be able to compare the time complexity of each. But my bet is that you're gonna want to use a linked list based implementation most of the time, just because it has a lower time complexity to it. The array-based implementation, I think, is more of its own little like interview problem, just trying to like manipulate an array to be used as a queue. So in general, you probably want to, if you just need to use a queue, you probably want to use a linked list based queue. But building a queue out of an array is kind of a nice exercise to do. There are also in whatever your language of choice is. I know Python has one, other languages have their own. If you're building something off of a queue, you probably don't want to build the queue yourself. You'll want to use whatever language you're using, its implementation of a queue, so you're not, reinventing the wheel.
I have a small question. So, if you do like an arrays-based implementation, then even like, so when you enqueue, the time complexity would be O of n, right? Even if you're just sticking it to the front.
Mm-hmm.
Oh, okay.
Yeah, and that's just because, with an array, everything is assigned a position. And when we stick something in the front, we have to reposition every other item. Does that make sense? Or do you have another question around that?
I'm just reading the comment from Dario, and I'm just thinking, so if you use a linked list, when you insert, I guess that would be I guess that would be time complexity O1. But when you remove, wouldn't it be O of n?
Let's actually, let's go to the next slide and we can talk through that, because that's a great question. So what you're talking about is this bottom half here with the linked list based implementation. So the operation when we dequeue is actually a little simpler, because we're taking from the head, not from the rear. And since we have a pointer to the head, we just, return that element and reset the head pointer to the next element. Does that make sense why that would be O of 1?
Yep.
Cool. And then with the enqueue process, we're adding something to the rear. So we can make some optimizations here for space complexity over time complexity, depending on what we're looking for. So if we use the most basic linked list implementation, it's going to be O of n, because we're only storing the head pointer. We have to traverse all the way to the rear and then add something to the rear. But if we want to, add a little more space complexity, aka add a pointer to the rear node and just keep track of that as well, it becomes an O of 1 operation, because all we have to do is find the rear node that we have the pointer to, change the next to be the item that to point to the item that we're adding, and then change the rear pointer to the new final item. So that's just a trade-off you can make based on whatever implementation is helpful for you. I will say usually, adding the space complexity of 1 pointer is a very low cost to pay for changing something from O of n to O of 1. That's a pretty excellent benefit. And then just looking over the big O's for the array-based implementation. So what we just looked at is the second column. The implementation we just made is where the front is at the end of the array, because we're popping things off of the end and adding things to the start of the array. So this means that, like we said, the push or the enqueue method is going to be O of n, because we have to insert something into that 0th position and shift everything else over. And the pop dequeue is just O of 1, because we're just popping something off of the end. Our array already has a pointer to that. Now shifting over to this first column and thinking about, okay, what would the time complexity be if the front was at the beginning of the array? So in this case, when we enqueue things, we add it to the end of the array. When we dequeue things, we pop the first element off and shift everything else over to the left. So the complication here is that when we push or enqueue, we are just adding something to the end. So on average, that should be O of 1. But the complication here is because, you know, an array has kind of at least in most languages, kind of, in Python, it's a kind of a secret max length, but it still has a finite space that it has to take up. So whenever we're adding an element, every once in a while, we're gonna hit the like maximum size of the array, and it's gonna, the implementation of that array is gonna have to add a bunch more spaces. Usually array implementations, just when it hits the maximum, it doubles its size, which means that we are then doing O of n operations, because we're just adding the same number that we already have, and then doing the O of 1 operation of just adding something to the end of the list. Does anyone have questions about that? I know that can be a little confusing, but does it make sense why this on average is an O of 1 operation, but every once in a while when we hit the max of the array, it becomes O of n?
I think it makes sense, especially after you learn about how memory is managed. It makes sense that at some point you just run out of space and you had to get more space. So
yeah, it's very under the covers, but that's kind of what's happening under the array implementation. And then of course when we,
oh sorry, I was
that?
just gonna add a note. Totally, like it's all like all under the cover. For example, like Python also has like a data structure called deck, which is like a variation of queue. But when you actually look at the underlying source code for how deck is implemented, it's actually using a double linked list so that you can get O1, pop, and push with this kind of data structure. So yeah, most of the time, linked list based implementation is going to offer you this kind of like a time complexity advantage. And then you might be wondering then why, bother using array based implementation. I think for just purpose of understanding, this is still helpful to know. Just because, like, hey, like if you are like actually inserting something to like the header array, make sure that it's not actually incurring like additional time complexity, right? And different like languages have like different implication. For example, in Python, if you do that, you're gonna incur like this expensive O of n cost time operation. In JavaScript, it's like a little confusing because even though JavaScript has an array, the underlying implementation is kind of like similar to linked list. So it has still has like O1 like push and pop. So it really depends on language to language. But do know that some languages, the array-based implementation could have that extra runtime. So
nice. Yeah, that's good detail. Thank you. And then, like we talked about, if we are popping from the array-based implementation where we're popping from the front, obviously we grab that first element and then we have to shift everything else over. So that becomes O of n. All right. Everyone's favorite time complexity. I know that can sometimes be a lot, but it sounds like y'all are getting it. Y'all are smart. So next, we want to jump into just a little sample problem, and this will be building on what you just used using stacks. We want to build a queue using stacks, and you might think, why would we do that? Stacks are kind of the opposite of a queue. Well, one, it's fun, and two, in this problem, we actually get to use 2 stacks. So we're kind of trading off memory complexity for this will save us a little time. So the problem here, we want to implement a queue using only 2 stacks. And obviously we want to try and make that as low time complexity as possible. You can kind of think of this, a lot of the good stack analogies that we've been using could be helpful here. Think about if you've got, let's say we've got two stacks of pancakes, or rather, we've got two empty plates that we can stack pancakes on. And you want to come up with a method where you can easily take the first added pancake off of the stack without having to dig through the stack and get to the bottom pancake. So if you've got two plates, what's an algorithm you could do in order to ensure that the first added pancake ends up on top of this stack? And I think I will pause here for a little bit because I want to give y'all some time to digest and just a little bit of time to think about this yourselves. Obviously, I have an example of what this class could look like here. But I think the most important part to start with is just visualizing in your mind two stacks and trying to figure out like visually what that algorithm is to turn two stacks into a like workable queue implementation. And if you feel like it, you can definitely, pull up your IDE and code a little bit, but I'll give us, let's see, it's 11:30 right now. I'll give us 5 minutes just to think about this first. I think that the first thing you want to do is maybe diagram your solution a little bit, do some drawing, and if you are up to it, go ahead and code, but mostly we want to think about the strategy here. So let's come back at 11:35. And any questions before we go, also any clarification questions on that problem? All right, I'll take that silence as you're already working on it. You're getting a head start. So yeah, I'll ping y'all back at 11:35 and go ahead and think about this one.
Okay, so I have a question.
Yeah.
So are we adding so are we adding each element from the two stacks to our queue?
No, the two stacks are what's going to make up your queue. So I'll give you a hint like this in this initialization method here. Actually, why don't I? That's the answer. Okay. In this initialization here, you're just going to initialize two stacks, or in this, like two arrays is kind of the easiest way to do that. So under the covers of your queue, the only memory you're going to take up is two stacks. Does that make more sense? Less sense?
I think it makes a bit more sense.
Just going back to like the real world analogy, this would be like, just imagining like you should have like two empty Pringle containers, and trying to kind of like recreate, okay, well, if I want to get the chip at the bottom first, how can I kind of utilize those like two containers to kind of recreate that kind of behavior?
Mm-hmm. All right, we're at 11:35. I want to check real quick. Is anyone like in the middle of a thought that they want to finish? All right, we'll go ahead and get started then, if that's all right. First, I'll open up the floor if somebody wants to kind of describe an algorithm that could maybe do this, or even wants to just bounce some thoughts off and try and think about how we might do this.
Yeah, I kind of thought like you could append the second stack onto the first stack. It might, I don't know, it might look different if it's an array versus a linked list. So if it's an array, you could just append, whereas if it's a linked list, you'd point the tail to the head of the second stack. And then you'd reverse the new stack so that the operations can be the opposite. So the pop operation now pops out from the end, and the add is to the front of the new stack, which has now become a queue.
What do you mean by append here? Like joining the stacks together?
Yeah, yeah.
Okay, so when you, I guess, walk me through when you add an item to this queue implementation, what happens to it?
When you add an item, yeah, so now it's you'll have to add it to the front of the queue instead of to the wait. Yeah. Wait. Last in, first out.
Yeah, so we have two
to the end, sorry.
And so which, I guess we don't have, we're implementing the queue. I think I might not have totally been clear about what we want to implement is like an algorithm for adding and popping things off. We don't necessarily, we're not too worried about like taking existing information and rearranging it.
Okay.
Yeah, sorry, that might have not been as clear as I would have liked. So what we want to think about is like, we have two, let's start with empty stacks. We have two empty stacks. We want to, I mean, when we add one item, there's not much complexity going on. If we add another item, we want to figure out how, like what algorithm can we use so that the next item we pop off is the first item we added, rather than just placing that second item on top of the first. Does that make more sense?
Yes, so reversing the operations.
Reversing the operations. What do you mean by that?
Of the stack to become the queue.
Yeah, exactly. So yeah, with the stack, we, you know, put the most recent things on top. We want to use our, you know, multiple stacks to reverse the order of things, basically.
Okay.
Yeah.
I have a terrible idea if you want to hear it.
I always love terrible ideas.
I think we keep the push function just the same, but whenever we're going to remove something, we have an array that a stack that's empty and a stack that has all of the information. We go through that stack that has all the information and put everything on the stack that's empty, and then remove from the stack that was empty. And that's going to give you the first value, which is now the last value. And so you basically split everything. It's terrible, but it works.
So you've got stack one that has, let's say, A, B, and C in it. A is your first item. So you're saying when you pop, you're moving everything to stack two and then taking the last item off?
Exactly, yeah.
Okay. So we're putting all of the complexity into the pop operation then. Is that correct?
Yeah.
Cool. I think that like is potentially a solution that could work. The one that I'm going to present to you, we kind of do the opposite. We put all of the complexity into the push operation. So let's walk through how that will work. Obviously, we have kind of two conflicting things here. We're using stacks, which are last in, first out. And we want to build something that's first in, first out. So these stacks just need to reverse the order of the elements that we're adding in order to make it a queue. So since we have this extra stack, we can kind of use it. And again, for this solution, we're putting all of the time complexity into the push operation to make the pop operation easier. But there definitely is an implementation where you make the push operation simple and the pop operation is where all your time complexity is. You know, dig to the bottom of the pancakes and grab that bottom pancake. That's an implementation. We're just optimizing for different things. So let's walk through the strategy real quick. We've got item A in the stack and we want to add item B. We don't want to add item B on top because that would then be the one we would pop off. So let's first move item A over to stack 2 to make way. Now we can add item B because we want it to be on the bottom. And we can just move item A back over to item B. So we're basically emptying out the first stack, making way to add our new item on the bottom of the stack so that it will be grabbed last. And then we're moving our first item or first items back over. So I want to pause there and look for a second. The implementation, these I think are relatively simple. We'll go through those, but I think what I especially want you to think about is what's the time complexity of each of these operations, especially the push and the pop operations. What do those end up being? So like I said, our initialization is easy. All we're doing is making 2 stacks, or in this case, 2 lists. The push operation is where all the complexity is. So this is kind of the fancy Python lingo I was telling you about. And I'll break this down a little bit more because I know it can be confusing. But we are evaluating stack 1 as a Boolean. So it will tell us whether or not stack 1 has items in it. So this condition is just saying while stack 1 has items in it, we are popping items off of stack 1 and appending them to stack 2. So this is that shifting operation where we're taking everything from stack 1, putting it onto stack 2. So we're taking all of our pancakes on stack A, on plate A, and we're moving them over to the other plate. And now all we have to do, we're at the bottom. We know that stack 1 is empty, since that's the only way we could exit that while condition. So we append our new item to stack 1. And now we want to do the opposite. We want to take everything from stack 2 and move it back over to stack 1. I'll open this up for questions, and also actually, let's do it this way. Instead of one person calling out the time complexity, would y'all want to write in the chat what you think the time complexity of this is? And I don't have multiple windows, so I'll have to be creepy over here. But let's see. Sorry, I'm trying to be able to look at the chat and also allow you to look at the problem. But yeah, I'll open it up for questions if anybody has some. And then when you think you know what the time complexity of this is, the big O notation, go ahead and write that in the chat.
Valerie says quadratic in the chat.
Interesting. Quadratic. Valerie, do you want to talk that through? What in the problem is kind of pinging the quadratic?
Well, wait, I think Dario has his hand up. But I was.
Gotcha.
No, Valerie, sorry, that was for last. That was before for last question. I'm sorry.
Okay. Yeah, I was just thinking, like, every time you want to put in, and like, well, first of all, will be, I guess, appending the integer or the object. But like every time we do that, we have to go through the stack that we currently have, right?
Mm-hmm.
So wouldn't that be quadratic? Like, let's say we have an array of integers that we want to put in. So for each of those arrays, we'll have to go through then the stuff that we already put in the stack to put it to the other stack, and then put in the array the integer we want to put in, and then put it back.
Gotcha. So you're saying since we're moving through the stack twice, that kind of like in your mind pings the quadratic time complexity. Am I understanding that correctly?
Yeah, but I don't know. I think I don't.
Yeah.
Sure.
I see where you're coming from. I think the important thing to notice here is that the quadratic time complexity usually comes about when we are going through a list of things, and within each item that we're going through, we then have another like loop. So it's like loops within loops is where the quadratic time complexity comes in. You're right that we're going through things twice here, but we're doing it serially. We're doing it, we're going through everything to move it over, and then we're going through everything to move it back. So in that case, it increases the time complexity linearly rather than quadratically, right? Because we're just multiplying by 2 rather than like multiplying, n by n. We're just adding them together. Does that make sense?
Ariana in the chat also says O n plus n, since we're doing the operations for both stacks, but same, not sure. And then Dario also followed up saying that because it's 2n and it's O notation, that simplifies to just O of n, which is the right answer.
Yeah, y'all are killing it. Yeah, so let's, I have a slide for this later. We'll just go straight to that right now. So yeah, there's actually a much more detailed explanation for this because everything is complicated, but in the end, it boils down to O of n. So the, yeah, because we are both popping and pushing each element, it becomes 4n. And then the introduction of a new element adds a little complexity. This is more detailed than you would really need to give in an interview, honestly. But just noticing that there are multiple iterations that we have to go through, but they're not quadratic. They're not iterations within iterations. They're just linearly increasing the time complexity. We just end up with O of n because of that. Does that, again, this is the time complexity is kind of the beast of this. So I will pause again for any questions on that. All right. Let's see, we've got 10 minutes left. I'm gonna quickly go through the The push operation is obviously where all the complexity is here. So that's the important one to understand. The other ones turn out to be pretty simple to pop. We just pop off of stack 1 because that's where all the things are. And we put all the complexity into the push operation so that the pop is really simple. In order to peek, that's, we're just looking at the element. So we use the -1 index, which in Python, at least, that makes it easy to look at the last item in an array. And finally, to see if something's empty, we're again using this Pythonic language that says stack 1 is true if there are items in it, it's false if there are not. So we negate that in order to see if it's empty or not. All right. And obviously all of those are just O of 1 because we are using built-in array methods that are already O of 1. And then I assume these slides will be sent out at some point. These are some lead code problems you can go through if you want some more practice using queues, implementing queues, doing problems that kind of require you to understand queues. And then that is all I have. I'll open it up for questions now. Can be on the material, can be general questions. Yeah.
Looks like we have a question in the chat. Daria mentioned that we did linked list last time. Can we use a queue stack to find cycles? Oh, so yeah, this is a problem that was like posed last time in the last lesson slides, but it was like a problem around finding cycles in the linked list. I'm not totally sure if you can use like stack to find those things. I'll probably just stick to the techniques that was covered in the last lesson, which was like using like the slow pointer and the fast pointer to see if they will like overlap at any one point and see if there's cycles in there. For graphs, if there were to find cycles, there's another thing or algorithm called topological sort that can help you find cycles. In terms of graph, this will be a topic that we'll be going over in like, I want to say like lesson 8 of Techquitable, but we might cover some of those things. So you might see topological sort come up in that lesson. All right. Any questions about today's lessons on stacks and queues? If not, Chris and Alma, thank you for the wonderful lesson. And then with the remaining few minutes, so just wanting to kind of open up the floor to everyone to just like ask questions about, what is it like to work as a software engineer at your respective companies, or what's your journey been like, just like entering the software engineer career, just because Alma, like you're fairly still like recent into it, having graduated in 2018. And Carissa, you have like this interesting story of like, not kind of like coming from like a traditional path, which really speaks to some people a lot. So yeah, just wanted to like open up the floor for any questions about career path. And if there's no question, yeah, I'd love to also get you any kind of advices from Alma or Krista for those who are thinking about entering software engineers in engineering path. So.
What's it like working at Notion?
Yeah, so it's been fun. It's one of these companies that is not uncommon in that it's experiencing a lot of growth right now, tech companies. So it's gone from 50 people to over 200 people in the last year. And that growth is both chaotic in the fact that everyone's like new, but it also makes it a place that's just like a plethora of opportunities and interesting things I could take on. So that's my take, I think, in terms of when you're looking at different companies of different sizes, there's pros and cons to working at like a larger company versus a smaller company. And I think the like slightly under 100 number of people is when companies tend to be in this like rapid growth phase. And I think it's fun, but I was at a larger company before and I had a lot more mentorship, and that's like lacking here in comparison. But it's also, I think for me, the phase where I want to be taking on more as like a software engineer versus strictly learning from people that are more senior than me. I mean, that was a direction. I don't know if you intended when you asked. Notion also is just like a fun, I'd say software you could work on things that are like products that are geared towards other software companies versus products that are geared towards consumers or for us, it is just like everyday users. And being able to work on something for me that I can use and see the actual changes I make, I've realized I find very rewarding, even though I came from software from like a mathy side. On the flip side, I know other people more on like the infrastructure side get a lot of value from working on software and interacting with other software engineers as the end client. So knowing who your end user is and understanding where you derive value from when you're working in software is a pretty interesting kind of thing that you learn as you're on the job. Darren asks, how would you describe a good interviewer? Is it better to take first interview slots, or is it better to choose later times to prepare as much as possible? I think it's important to choose interview times that fit your schedule overall when you feel like comfortable and ready to take them on. Yeah, I think on the company side, the interview coordinators tend to be pretty accommodating. In general, I think the way they fill roles is naturally when there's a candidate that fits the role, whoever is the earliest will get the job, unfortunately. That's just the way that I guess like these rolling applications work. But at the same time, there's like a fair amount of concern that, or like thought that goes into making sure that we want the applicant or interviewee to be at their best when they're going through the interviews. So if that means like you have to reschedule an interview because you have an exam, I think knowing that you want to be your like best self when you're interviewing is like the more important factor to take into account.
Yeah, definitely agreed. I think also the sign of a good interviewer is that they like make you feel like they allow you to show your strengths rather than like, you know, honing on your weaknesses. But obviously there are a variety of interviewers. I think it's important that you know though that interviewers want you to succeed. They want you to do well in the problem. If there's something you're not understanding, don't get hung up on that. Focus on the things that you do well and make sure that you like show off all the things that you know.
Yeah. One thing I think is helpful is just talking a lot during the interview, and then the interviewer will try to latch on to you when you're like in the right direction or you're moving towards the right direction. So being attentive to what direction the interviewer is trying to steer you towards. They're being intentional because they want you to succeed. No interviewer is going to like try to trick you. They're trying to direct you towards like a question they have and seeing if you can answer it in the right way.
And if I were to add one more question, yeah, what was your interview preparation process like? And, you know, curious to kind of hear how much effort has gone in and yeah, any kind of strategies you use to do that.
Yeah,
when you go first.
Go ahead.
Okay,
go ahead.
Okay, I'll be really quick. When I was in the midst of interviewing, I was very much setting aside like at least 3 hours a night to practice interviewing. And once you hit the like on-site interviews, it's just like very time consuming. I'd say like multiple days a week were just spent like either leak coding or doing the on-site interviews. At the same time, the whole process isn't actually that long. So it wasn't more than like a month and a half for me, but it was like a very concentrated, this is what I'm going to be doing instead of socializing. And then it's unfortunate because it's not a skill you use as much on your day-to-day job, but like interviewing is just like weird subset of stuff that you have to learn just because that's how software engineering works, or how the software engineering job application works, at least.
Yeah, definitely. Yeah, I think I used a lot of the usual tools of like cracking the coding interview problems, reading through those and explanations, as well as like doing leak code. But I think the most helpful thing for me, honestly, was I had a good friend who, you know, helped me like do faux interviews and just like go through a problem that you might see in an interview, like kind of officially. That like really helped me work down my nerves for just like, you know, it's very different typing out a solution on leak code from actually like talking through something with someone. And like, I think a good pairing interview should be very collaborative, and you should be like bouncing ideas off of the other person. So if you get a chance to, obviously you can do that with your mentors here. I think just like doing kind of faux interviews was the most helpful thing for me, for sure.
Yeah. Also, doing interviews when I wasn't ready, when I first applied to companies, I wasn't ready and the interview went so poorly, was a huge learning experience. Like having a bad interview, even just like practice interview, or like maybe it was a phone interview that like went poorly. It's a lot you can learn from and like grow from and feel more motivated by. So don't feel like you have to ace every single interview. It's okay to like have some, like everyone fails an interview every once in a while, because it's sometimes you just don't know what the problem is. It's the way like these kind of interviews work, I guess.
That's a great point.
John says, I know it differs, but I'm wondering how many rounds of interviews on average you go through for an intern SWE position. Definitely varies by company.
Yeah, I went through 3 pairing interviews for my internship position, but I think it varies from company to company.
Yeah, I think I've done on-sites that like there might be maybe like 1 or 2 coding and then maybe 1 career-oriented interview. Other places are just the coding kind of interviews for like 5 of them, but they're all like maybe shorter. It does vary a lot by company.
Alrighty. Yeah, thank you for answering these questions. You know, really hope that these kind of responses or sharing your experiences help out the fellows here. I know we're already running over time, so gonna just have to wrap it up here. But Alma and Krista, once again, thank you so much for joining us today. And for the fellows out there, as we do every single week, the slides and the recorded lecture will be sent out in the Slack and as well as email. So please be on the lookout for that. But yeah, thank you. And I hope you guys have a nice rest of the weekend.
Thanks to all of y'all. Thanks for being here and engaged and asking great questions. Appreciate you.
Thank you guys.
Thank you. Thank you.
Have a good one.
Thank you. See you later, Alma.